Hello, math studs. We are back looking at probabilities. We're going to continue with section 8.3. We're springboarding off of what we studied with independent events. With conditional probability, things can get a little strange. Now, you can logic through this. I'm going to kind of take you through it that way. Looking at the formula for conditional probability can be sometimes a little bit strange, just depending on the situation. It's actually, I'm going to point all of that out to you when it gets a little bit weird. And it's really a language thing. It's really about how the problem is phrased, and then you trying to figure out and interpret what they're saying and then applying it to the formula. So let's start out this way. Let's go and look at an investigation. This is actually on page 377 in your book, and it's a nice little transition for you. This is an example of what we looked at before about students, what they study with biology, and then in this case, art. So both those things are going on. So let's just step through basically what we have here. We've got 100 students, and we see that there's art and there's biology, and then there's a crossover between art and biology, the middle part there, and then we have some students who aren't taking either one of those. So the universal number here would be 100, 36 of which they're not taking either art nor biology. So that's something to consider, although it's not going to necessarily play here. So the first question asking you, well, how many students study biology? You're obviously going to look inside this B part here. So we're going to be talking about those two numbers, 12 and 28. So we know that the number just for biology is the sum of those two, which would be what? What is that? That's 30. That's 40. Is that right? So now what we want to know is well, not only where is that in the region, where is that region? It's obviously all within B. They also want to know, well, of those students who study biology, how many also study art? Well, that's where the intersection part's going to come in. So that question right there is really what's in of, this is really in of A intersected with B. And that's just something to consider. We can just look at it and go and logically say, well, we know it's 12. So this question here is, how many of those biology students, how many of them study art? That would be the 12. And again, that we're in that region. Would that be in the Venn diagram? It's the intersection part. So what notation is used to represent this region? That would be that N of A intersect B. So what is the probability that a student studies art given that they study biology? So here's the key, the word given. That's creating this idea of conditional probability. We're just considering the biology students. What is the chances that they're going to study art? So to write that, we would say P of A slash B. That means the same thing as, that's the notation. That's the same thing as what's the probability that they study art given they study biology. So a way of figuring that should be, it should make sense then that to actually calculate that number is we need to know, well, what's the probability total? So how many total biology students are there? So in this case, probability A given B logically is there's a total number of 40 biology students. And of those biology students, how many of them are studying art? Well, that would be that 12 out of 40. That 12 out of 40 can also be found using the formula I'm about to show you. So keep this in mind. We'll revisit this here in a minute. So let's go back over and look at the definition we're going to use here. This leads into the formula. And the conditional probability goes this way. For events A and B, the probability of A occurring given that B has occurred. That's the idea of conditional probability. So we're given that B is taking place. So what's the probability of A happening? And this leads right to and right from what we just did. So we say this, the probability of A given B is the probability of A intersect B divided by the probability of B. So let's just record that in terms of the biology part of this. Let's go back over here and let's think about that. So it just told us that the probability of A given B is equal to the probability of A intersected with B divided by the probability of B. So when we look at it in this general sense, the question is, well, how did the 12 and 40 show up? And for most of you, you can look at that and go, well, that's pretty obvious, Mr. May. But I want you to think of it in this way. We actually end up with, I'm not trying to muddy the waters here, but we end up with this complex fraction because it's really asking, well, what's the probability of A intersect B out of the universal? So we got to still take into consideration of, well, what's the total number possible people in this whole thing? Well, there's 100 people. So knowing the universal number is important for calculating probabilities. And this is important for later on, not necessarily this example, but in other problems you're going to work. You're going to want to know, well, what's the total number we're drawing from? So we know that A intersect B, that probability of A intersect B is going to be this number of A intersect B, which is 12, out of how many total? Well, there's 100 total. And then we're going to divide that by, so we just calculated by taking 12 over 100, we just calculated the top part of this formula. So now, well, what's the probability of B? Well, there are 40 biology students total. So the probability of any student selected at random out of this is going to be 40 out of 100. So we have this complex fraction. Okay, I'm going to continue this work up here, follow my arrows. So really what we have is this. We have 12 100ths being divided by 40 100ths. And our basic math tells us that's the same thing as 12 100ths times 100 over 40, right? Dividing by a fraction, you invert and multiply, and you're going to see it. It shows up right there. There's that 12 40ths that we logicked through in the beginning. Now, you might be wondering, well, if we can just logic through this, why do we need the formula? Yeah, that's a great question. Like if you can logic through this, you can listen to the language and figure it all out from logicking through it, go for it. You know, if you can keep that all straight. But when in doubt, you can come back to this formula and rest assured it's going to take you there. Well, you know, if it's if the language is interpreted correctly. Okay. So, you know, I've been kind of hedging my bets with all of our discussion about probability, and it's what I led in with when we started talking about probability. Some of it's very counterintuitive. It can really mess you up. And it's really the counterintuitiveness comes from the language and how these problems are presented. So that's why I keep, you know, kind of, you know, soft pedaling this with, you know, with your thinking and how things can get turned around. It's just gentle warnings that, you know, you can mess things up if you don't mind your P's and Q's. So how do we apply this? Now I'm going to go through the example that's on page 387, and it's a nice process through really kind of everything that we've done so far, and then some, really. So let's just go ahead. I'm going to jump over here to another one that we've already pulled up. Maybe I can pull this up here. Okay, and so this is example 8. And example 8 is, let's make sure this thing's going to allow me to edit. Oh, there we go. I'm going to draw on this thing. Okay, so example 8 says, in this case, there are 84 teachers at a school. Of those teachers, 56 drink tea, 37 drink coffee, and 12 drink neither tea nor coffee. So at first glance, it's like, okay, we have these set of teachers, you know, some are drinking tea and some are drinking coffee. It doesn't consider a possible overlap. And so you'll notice here in part A, they've already started us with this. And I think this is good. It wants to know, well, how many teachers drink both tea and coffee? That's an important question. To be able to figure that out, you can use the Venn diagram that they have there, but I'm going to construct it to help us determine. That's not what I want. I'm going to build this for us, maybe. Hopefully it's going to let me do this. Oh, that's interesting. Hang on a sec. I am not quite sure why it's not letting me do this. Well, I guess we'll have to use this because it was letting me do that. One moment. Okay. Well, I don't want to start this video all over, so I may just take this same thing and open it in a different way. Let's do that. Thanks for your patience. We'll just do it like this. Oh, goodness. Glad you guys are patient with me. We're almost there. I promise. Okay, here we go. Let's do this. Come on. Yay. So let's create this Venn diagram again. So we're going to go right here. We've got those that drink tea, those that drink coffee. And we're going to use the information that they've given us to be able to construct this. And it's like, well, how did these guys go about this? How'd they get this 56 minus X, the X, and the 37 minus X? Well, we know from the information there are 84 total. So that's important. We know our universal number. So N of U is equal to 84. We know that overall there's 12 that don't drink either. And so we know that we have, from that, you should see that we have 72, because 72 of them are going to be in this tea and coffee and overlap thing. So tea and coffee together with the overlap should be 72. All right, so we know 56 drink tea and 37 drink coffee. And so our job is to figure out, well, what's between them. And you can use this little formula they have there, this 56 minus X. We know there's a total of 56 tea drinkers. And that's so why we want to say, well, let's let the middle be X. And if we take away the overlap, that X value, that leaves us with the 56 total. And likewise, we know there are 37 coffee drinkers total. If we take away the overlap, we end up with that. So all of this together should equal 72. So that gives us 56 minus X plus 37 minus X, all should equal 72. Okay, so it might seem silly why we're doing this, because you can just like take away the X's, that's fine. So we have 56 plus 37 minus X. Well, 56 minus 37, what is that? 80, 93. Make sure I did my math right there. I think that's right. And so then we've got 93 minus X is equal to 72. Subtract 93 from both sides, so we get negative X is equal to negative, what is that, 21? Make sure I did my math right here. Yep. And then, so X is equal to 21. So our overlap is 21 people. And so now we can recreate this so that it's legitimate with its numbers. And so we don't need this anymore. I'm going to erase this out of here. And we can do that process. We can go, okay, well, this is 21 in the middle. And then that leaves us with, away from those 56 tea drinkers, what is that? 35 of them are exclusively tea drinkers. And then we can go 21 away from the total number of coffee drinkers being 37. There are 16 only coffee drinkers. Okay. And so 35 plus 21 plus 16 should equal 72. You can do the math there. You can check that out. This should be rock solid. All right. So now really let's get to the whole thing here. What's the probability? Now we're asking the question, well, what's the probability that this random teacher drinks tea but not coffee? They drink tea but not coffee. Well, that should be pretty straightforward. There's 35 of just exclusive tea drinkers. So part B, we haven't even gotten to the conditional part of the questions, should be 35 out of 100. Oh, sorry, out of the 84. Because we're talking about just those folks, not 100. I think I said that before. We're talking about just the folks that there's the total number of 84. All right, 84 right there. See, our universal is 84. All right. C then. What's the probability that they drink tea and coffee as well? Drink tea and coffee. So it should make sense then that this is now asking a question that's conditional. This is actually the probability that they drink coffee given they drink tea. So C, this is an interpretation problem that I was talking about earlier. This is really being phrased. What's the probability that they drink coffee given that they drink tea? So we're going to use this process. So this is the same thing as, I'm going to use the formula, probability of the intersection of those two divided by the probability of just tea, drinking tea. All right, let me clear some of this out of here. Getting all bunched up, messy. Okay. So again, if you want to logic through this, you can. I'm not going to. I'm not going to logic through it. I'm going to strictly stick to the formula. Well, what's the probability of C intersect T? Well, that's that 21 out of 84. So that would be the intersection part, 21 out of 84. Divided by, well, what's the probability that they just drink tea? Well, what is that? That's that 56. That's going to be 56 then out of 84. I'm going to show you a shortcut. Complex fraction, the denominators are the same, and those two fractions, you can just cross them out. They just cross out, and you're left with the tops and the bottoms. So the 21 over 56 results. There's that probability that they drink coffee given they drink tea. All right, so I'm going to leave part D for yourself. I want you to go through that on your own. You can look at their example. I'd challenge you right now just to do it without looking at what they did. But now it's like the not. So this is phrased really as a conditional probability. They don't use the word given in this case. Hey guys, good luck with conditional probability problems. I will see you in class, if not in the next video. Have a fantastic rest of your day. Thanks.